My name is Colin, and this session is about understanding iModel data, and it's an introduction to BIS. This session is going to cover the basics of modeling data with BIS, the engineering domains that we have in BIS, some demos showing you how to use these schemas to actually build intelligent and smart applications, pointers to where you can learn more about BIS, and finally a call to contribute back to BIS. What is BIS? It's the base infrastructure schemas. This is a family of schemas that we use for modeling infrastructure digital twins, and it defines the iModel database format. BIS is open, extensible, and programmatically discoverable. What I mean by that is you can query an iModel and see what schemas are in it. You can query the schema and see what classes are in it. And you can query a class and see what properties are in it. And it's extensible because you can create your own schemas that build on top of ours. You can extend schemas that already exist once they've been imported into the iModel. And it's open because all of Bentley's BIS schemas are checked into GitHub and they're licensed with the MIT license. So let's go over some BIS basics so you have some groundwork when you go and look to find more information about BIS. The first thing that you got to know with BIS is all data is stored in elements. It's a single, small, uniquely identifiable thing in an iModel. And you can extend an element by creating element aspects. These are optionally applicable sets of properties that you can apply to any element. So if you want to add some more properties to an element, you can create an element aspect class, add the properties to it, and then attach it to an element. And it acts as though it's part of that element. The final class that I want to talk about is model. Model is a container for elements. So every element exists within a model. On top of these three classes, there's three relationships that are really important when you think about how the data is organized and structured inside of an iModel. The first one is element parent-child relationship. This lets you build assemblies of elements. So you can take a bunch of small components and build them together into one larger assembly. Next is model contains element. This is the relationship that identifies which model an element belongs to. And finally, this one's a little bit tricky, is model represents element. What this is a way to break down an element into smaller components in a submodel. So if I have an element that represents a building, I can have a submodel that represents the building in greater detail. This is a really powerful way, and you can see how we use this a little bit later on. Now, in addition to those classes, there's a whole bunch of things that come out of the box with BIS, and I'm going to mention a couple of them here. First one, all values are stored in SI units. So you can be confident that no matter what the value is, if it has units, it's stored in SI units. And by the way, because BIS is queryable, you can always query to see what unit some value is stored in. Is it in meters? Is it a volume in meters squared? You can find that out by querying the metadata information within the iModel. Next, we have a bunch of standard ways to store common values and common concepts, and I'll highlight three. One is codes or tags. So like think of a pump tag in a plant or a room number in a building. These are generally human readable things that you can use to identify some space or some element within a structure. Next, we have federation GUID. This is a really powerful tool that comes out of the box that lets you federate an element with some external representation of that element. That's good. Next, we have user label. This is really simple, but it's actually really important. This, along with the code, always gives you a user-friendly way, a user-friendly label to show when you click on a particular element. Next, we have a bunch of standardizations when it comes to things that are oriented in space, things that are spatially located, and our geometry format. So if you have something that's spatially located, it's in our spatial index, which means you can do fast and efficient queries to find things within volumes. Its orientation is stored in a standard way, and the geometry is stored in a standardized format that you can break open and use with our API. Next, I'll highlight the type definition system. There's other similar definition systems, but the type definition system is really important. It lets you take things like catalog items and bring them into the iModel. You can also create your own reusable components that you'll then reference in other elements. And finally, I'll highlight the material system. This is a physical material system, is probably a more accurate word. This lets you identify whether something's concrete or or steel or asphalt or what have you. There's a standard way to do it all throughout the system. So no matter what schema you're dealing with, you have standard ways to figure out all these things and more. Now, we'll talk a little bit more about extensibility and really hammer this home, because you can create your own specialized element classes, your own specialized parent-child and referencing relationships, create your own totally custom relationships. You can create structs for complex properties. You can create enumerations. You can create custom units. So if there's a dimension that we don't have support for out of the box, you can add it. And all these things are queryable. So if you do add someone else can query to see what they are and work with them programmatically without ever knowing that you made the customizations. These are really powerful tools, and we leverage all of these in-house when we bring in your data via connectors. So this is something that's battle tested and true, and a really crucial part of the iModel story. Now, we've gone over some basics, but I want to go through an example of how you might actually model something in BIS. BIS takes some real-world physical object and models it in multiple perspectives. What does this mean? This means we break things up into different groups of different concerns, and that lets us model things, A, with a lot of detail, while still keeping things organized. B, it allows us to add more detail later without modifying what we have already there. So let me give you an example. You might have a physical element that describes its 3D geometry. You might have a functional element that describes its functional geometry, its function within, say, a plant and its requirements. And those things are connected together with standard relationships. I'm going to dig into this in an example right now. So we'll start with a pump. This is a real pump, or at least a picture of one, and we'll represent it with a physical element inside of the model. Now, this physical element is spatially located. It has geometry that will represent to the user, and it has properties that are relevant from the physical perspective. Next, there's a functional element that represents the function of this pump within the plant. Here I'm showing the drawing element, which is also connected into the functional element, but it provides a visual representation. So you have all three of these things all three of these elements that are connected together, and these three perspectives help make a more full picture of the actual pump that's being represented in a plant. Now, in addition to that, there's other things that get connected to the elements. One would be the category. So this pump is in an equipment category, and I can easily and quickly see all the other equipment that's in the plant. It's also going to have a type definition. This type definition element points back to the actual catalog item for the real manufactured pump that's going to be placed in that plant. So with all of these multiple elements connected together, we get a really rich view of this one single pump. And remember, this is all discoverable and queryable because we're using standard relationships to connect the elements and standard base classes, so we understand that something's a physical element or a functional element or a type definition element. Now, I want to talk about one other important way that we do modeling inside of BIS, and that's modeling in increased levels of detail. So the top level, at the very top of an iModel, we have a subject that defines what's going to be in the iModel. That's called the root subject. This tells you what the iModel is about. And think of it as a plain text description, one sentence description of what this iModel is about. And we have child subjects, which are connected via the parent-child relationship, that further organize the contents of the iModel. I think the best way to think about it is the way you might organize a series of DGNs or DWGs in a project. Because this is how we expose the data when it comes from connectors. Because that's what we have from the connector point of view, and it's something that you can update later. But think of that organization that you might set up for a project, and we capture that with the subject hierarchy using the element parent-child relationship. Because since it's data, subject is, of course, a specialization of element. Now, the subject hierarchy ends where the modeling begins. So when we actually go from a tree of the files to the actual contents of the files, if you're thinking about it from the connector case, that's where the modeling tree ends, and the actual elements containing the 3D geometry or the functional definitions, that's where they begin. Now, I want to talk about BIS domains, because of course, saying something's a physical element, that's not really very rich semantically. We've got dozens of release domains that cover specific disciplines. For example, building or rail and road. And we've got multiple new schemas under development now. These release schemas are actually in production with users, and our connectors are building on top of them to create the rich semantics coming as they exist in the original files, and building on top of that with additional standardization. So in addition to the released and work in progress schemas, we're actually making updates actively to these release schemas. So they're not one and done, they're being enhanced as time goes on. Just to cover some of the disciplines that are there, we have building schemas, civil, construction, earthwork, structural analysis. In addition to these discipline domains, we have common domains that span disciplines. And these are really helpful because different disciplines always used to model these common things differently. In BIS, we're modeling them the same way, so that way it's much easier to reuse stuff and have one combined picture of your asset and your digital twin. One of these is classification systems. So if you want to represent omni-class or unit-class. Another one is distribution systems, profiles. And I'm going to highlight spatial composition because this is one that I'm going to dig into in more detail. Spatial composition, of course, gives you a view, a breakdown view of the contents of your iModel grouped into spaces. So now I'm going to get into some demos. All right. So the first demo I'm going to show you starts with the iTwin viewer created with our Create React App template for iTwin. So I've basically taken this sample directly and I've added one single widget that lets me emphasize things based on spatial queries. Spatial composition queries. So let me hop over into that. So the first thing I'm going to do is I'm going to hide the widget that I created so we can focus on what you get out of the box with the iTwin viewer. So you can see we have a 3D model here of a building. It's been spatially located on the Philadelphia River waterfront, on the Delaware River. And if we look over here, we can see the subject hierarchy is manifested via the model tree. So if you see here, you can see there's DGNs, and we go down to different levels. This was the layout of the files that the connector ran against. Now, I'm going to hop over into the spatial containment tree because that's what we're going to dig into a little bit more detail. So we start out with the site. Below that, we have the building. And in the building, we have one story for each story. I'm going to go onto the roof here, and I'm going to select this space. And you can see it has selected this equipment room up here. And if I expand this and take a look here, you can see here's an actual door within that space. Now, how did this get built up? This is built up using queries into the iModel. And so I'm going to show you the schemas that we use for these queries. So I'm going to hop over into our Schema Explorer, and we're going to start by taking a look at the building spatial schema. This is a really simple schema. It's got just a couple of classes, but what it lets you do is identify spatial containment things that make sense for a building, like a building or a story or a space within that building. I'm going to look at story because that's what we're going to use further on in the demo. If we click over into it, we can see that this is a spatial location element. So a spatial location element is something that exists in real physical space but has no mass, so a volume. And that's just what a story is. If we expand this more, we can see the drive class created by the connector that represents the floor as it was in the original application. So it has additional properties that are added based on what was in the source file. So we bring all the data that came over originally here. Now, while we're talking about story, we're talking about spatial location elements, I want to talk about another spatial element. It's just a little side note here. That's a special physical element. So a physical element is something that exists in space. It has mass. It's a real thing. So we've got a door here, and we showed that door moments before, and it was of this door class. So this is the basic door class customized to add the additional properties that are needed from the source file application. So now that we've taken a look at that, I want to hop over into our iModel console. This is a great application that lets you run ECSQL queries against the iModel live. So what's an ECSQL query? It's a SQL-like query that instead of querying for tables and columns, you're querying for classes and properties. And instead of querying for linked tables or foreign keys, you query for relationships. So this is a really powerful syntax, and I'm going to show you a couple queries here. This query uses a standard relationship that talks about how a spatial location element overlaps other spatial elements. So in this case, we're talking about a story overlapping spatially located elements that exist within that volume. So I'm going to run this query real quick. And you can see that I return back a bunch of EC instance IDs. These are IDs, every element has an EC instance ID, and these IDs are unique for every element. So this is a great way to identify things and select things. And we'll use this a little bit further on in the demo. And then you can see that here's all the different types of classes that are within the roof space. So we've got walls up that are up at the top of the roof. And there's various other things in here. So let me hop over into the actual demo application and show you how we're going to leverage this. So I've got a bunch of queries here that are the same as the one that I just showed you before, but I have one for each level corresponding to this tree over here, okay? So if I apply emphasis here, we're going to go through and we've created a visualization that categorizes every element by the space that it's contained in. So you can see this is really powerful and it's really simple. All I did was execute some queries, get the instance IDs back, and then emphasize the elements based on the query results. So this is really powerful. And if you want to see some more about spatial location, I will point you to where to find those docs a little bit later on. Now I want to hop into another ECSQL query, and this one is to show the spatial containment tree, or sorry, to show the subject hierarchy that for this model based on, so it's basically this model format printed out straight to the console. So what I've got here is a recursive CTE query that joins and creates a path that shows the path from the root all the way down to where modeling actually starts. So I'll run this query, and if you take a look here, you can see here's the final model, and then within it, here's the path from the building down through all the separate levels of hierarchy that we have down to where we're actually going to get elements. So the submodel below this element here, DM structural, what have you, is going to be the actual, it's going to contain actual elements for the structural model here. Now, I want to do one more query before we move on here, and that is to show you how you can do ECDB meta queries. So what is ECDB meta query? This is a query that queries the BIS classes, schemas, properties, everything that's in the iModel. So this query that I've done here is to show all of the classes that derive from classes in the building spatial schema. So I showed that story has a custom class called floor, which is its child. So if we run this query here, you can see that we have story, which has we have floor, which has a base class of story, and that's what we saw in the schema editor. So I just want to show that all this stuff is programmatically queryable, and that's really powerful. Not only can you query the data, but you can query the metadata. And so I haven't shared the source code for this application because it's not really very nice code. It's pretty rough. But if you go over here to developer.bentley.com/samples, you can find a similar source code that's much nicer and cleaner to show you how to emphasize elements. And here's another one relating to something we talked about earlier, and that's the spatial index. So this shows you how to use spatial queries to quickly select things based on volumes. So the next thing I want to show you is the actual BIS schema repo. So here it is on GitHub. It's public. We've got issues that are all in the public. We've got pull requests that are public. We've got public milestones that you can contribute to. You can open the discussion question, all that stuff. We'd love to hear from you. And we're doing this all out in the open because we think it's important that you see us do all of the development, not just see the end product. So next, I'm going to show you some documentation and point you to where you can go to find more about BIS. So first thing is go to itwinjs.org, click on Learning, and then click on BIS, and you'll get here. So this is a set of documentation that explains BIS in tons of detail. I went really high level to kind of give you an overview, but this is some really good detail that you can use to understand BIS. And we go all the way from the conceptual here down into the very specific here. So this is the documentation for the classification system schema. Remember I said this is how you can represent something like omni-class or uni-class within your iModel. And we have a description about the schema. We have instance diagrams and class diagrams. And then we have essentially generated class docs that tell you every property, everything about the property, its inheritance, all that kind of stuff. And we're working to improve this continuously. So we'd love your feedback on this documentation. We'd love you to come and contribute to us on GitHub. And I got a couple more things to go over. So, like I said, we want your input. Come and contribute to BIS schemas on GitHub. And one thing in particular I want to highlight is our IoT schema project. We have a bunch of work in progress schemas for doing functional and physical definitions for IoT devices. This isn't about storing IoT data inside of an iModel. It's about storing the location and functionality of IoT devices within the iModel so that you can then connect it to a system that stores the IoT data. So this lets you build integrated experiences where you're pulling IoT data live into a digital twin. So this is work in progress now. We've got a milestone out there. We've got some pull requests out there with work in progress schemas. And we really want to hear your feedback. We've brought it to people internally who work on IoT. We've done collaboration with some external sources privately, but we'd really like to do more out in the public. And so we'd love your input. If you don't have anything to input on IoT device schema, let's come look at our other schemas. We have other stuff that's under review now. And we'd even like to hear back about issues with our documentation, things that you find unclear. We really want to hear from you. Now, I'm going to blast up a couple links to see stuff that I've talked about here. First is github.com/itwin/biz-schemas. This is where all of our schemas can be found. You can also find all of our schemas published onto NPM. We've got our documentation at itwinjs.org/biz. The iModel console, which is a really great tool for playing around with ECSQL queries and getting to know the data in your iModel better. We've got the iModel Schema Explorer, which lets you view the schemas visually that are in any particular iModel. And if you go to iModelSchemaEditor.bentley.com, you can see all of the standard BIS schemas without any login. Because once again, we really think it's important to do this stuff out in the open. Next, we've got the emphasize element sample. So this is all the code that you need to replicate what I did in your own application, although it will, I'm sure, look better than my horrible attempts at UX. And finally, get involved in the IoT schema development. We'd love to hear from you. And with that, I want to say thank you very much, and I hope you enjoy the rest of the presentations today.